We are living in a world that is warming up, and there's every proof of that has been given. And it's not just stopping here. We also know why it's happening. We know it's happening because the amount of greenhouse gases in the atmosphere is steadily increasing. On top of that, we also do know that the changes that are coming ahead because of that are very likely to exceed 2 degrees if we are not constraining the emissions actually very, very clearly, that we are stopping up within the next 30 years to basically go in zero in terms of emissions. That is the 2-degree target, and it can only be reached that way.
While we are sorting this out, I would like to just say a few words already, which is just illustrating the idea of the urgency. Of course, I'm sure I don't need to talk much about that here in this meeting. The whole setting, the whole program is very much lined up to exactly feed into the urgency. And yet, I'd like to motivate it through a number of developments in recent year and actually also now. But to do that, I will try to very briefly go into a little bit of the actual climate physics, the what's going on with our climate system, which is of course what is motivating a meeting like this and all the activities that are ongoing internationally and at local level. And so the climate issue in a nutshell, I try to put that in one, I think, very important illustration of what the issue is. And by doing that, I also like to just give a few reminders about the process that put a lot of this in context, namely the fact that the climate agenda has existed at least for 25 years through the scientific community that's contributed to the IPCC reports over the years. And then I will go very traditionally through some of the observed evidence we have for the changes that are ongoing on this planet, and dwell a little bit on how we understand it in terms of the science today, what it is we see, and then of course towards the implications of why this is important, because we actually have something in the horizon that's coming up, and that's looking into the commitments that we've already have done in terms of emitting greenhouse gases to the atmosphere over centuries already, and what the projections for the future are. A lot of this, I'm sure most of you have seen in one way or another, but bringing it together, I hope that this will give you the framework for what you are about to discuss throughout the rest of the days here. So I'm going to throw you directly on a diagram that appeared in the most recent IPCC report, which is actually my recollection of what climate change in a nutshell should be thought about. Is not talking so much about global warming and what causes it. This is just in terms of combining evidence from observations and projections from advanced modeling studies. And for now, you don't have to think very much about the sort of cloud of information here, but just think in terms of the lines drawn. And as usually, this is looking like a straight line, so it's a very boring graph. But it starts out from 0.0, and then you have a basically linear increase. And the important thing is, of course, is what is on the axis here. So on the horizontal axis is shown the cumulative total anthropogenic CO2 emissions since 1850. And on the vertical axis, you see the global mean temperature change compared to same time, 1850. And what is evident from this diagram is that the last 100 years, or 150 years, which is represented by the black line, starting at 0.0 and moving forward. And there is a dot for each decade. But you've seen that we now reached a level where we've combusted carbon from fossil fuels to the level of 500-600 gigaton, which is just since basically we started the Industrial Revolution. And overall, the global temperature in that period had risen by approximately 1 degree. And you combining information from all kinds of simulations of the future in different emissions, the interesting thing to note here is that there's a blue set of lines, dark blue, that takes off from present day and keeps the temperature below 2 degrees. Then there's a pale blue that goes further on, an orange, and a red line that ends up at something nearly like 5 degrees. And what you can see from that is that there is no time axis on this. So it's in fact, despite the fact that these scenarios actually represent a time evolution, the neat thing about this diagram is that they're in immediate translation from the amount of emissions that we can allow ourselves if we want to keep the temperature below a certain threshold. And as I'm sure you're aware of, the 2 degree has been identified as sort of the target. But you can also see from this diagram that this is a very, very demanding target to meet. We've presently used like 60 to 80% of the total allowance we have in the bank. And so we have to find out how we spend the last 20% if the 2 degrees is the target. And we have to do that in a very efficient manner. So a lot of what I'm trying to do is to give you some input to how this graphics came about and what the 2 degrees means and in terms of the urgency. So of course, what is this thing with the relation between global temperature and anthropogenic effect is something that we've seen Al Gore, we've seen a lot of people showing. On one hand side, we have an increase of greenhouse gases in the atmosphere, and at the same time, we also seen an increase of temperatures. And these are kind of graphics that's been around for a long time, and it's still somewhere and places that this is discussed whether we can actually attribute the cause of the temperature change to the changes in the atmosphere. I don't think I need to give you the arguments in this room, but if you look at the way that you can even discuss whether we can calculate the temperature of the planet correct, and many different groups are doing this. So if you could see it from the back of the room, there are actually 3 curves on the temperature lines to the lower right here, but they are almost indistinguishable. They're constructed in different manners, and the sort of long time changes are much more dominant than what you can see depending on methods to calculate the mean temperature. And it's also interesting to look at in the sort of more recent terms. This discussion is still ongoing whether, if we look at this now for the last sort of 15 years, has been discussed whether temperature is actually rising. If you look at this isolated, it looks like if we were only having data from like the late 90s until today, nothing is really happening. But I'd just like to inform you that that story is over and gone. We are now entering another era where temperature is really going to pick up again. And this year, with data on only until August, we have records by record by record by each month, and temperatures will pick up. And my prediction is therefore that in the next 10 years, I will have to answer questions about why the temperature hasn't risen since 2015. So putting this in the IPCC context, the Intergovernmental Panel on Climate Change is an intergovernmental body which has within the UN system is established in order to inform decision-making and governments on the role of climate change on all aspects of the whole thing. That is, what causes climate change, what are the impacts, the consequences, and what can be done to reduce these consequences and avoid future changes. So in its first report in 1990, the contribution from Working Group 1 stated, and I just quote this, "These increases in greenhouse gas concentration will enhance the greenhouse effect, resulting on average in an additional warming of the Earth's temperature." And that's sort of a very clear and blunt statement that was issued back in 1990. This has been revised a little bit over the years, but 2001, there's new and stronger evidence that most of the warming over the last 50 years is attributable to human activities. And in the most recent one, human influence on the climate system is clear. This is evident from increasing greenhouse gas concentrations in the atmosphere, positive radiative forcing, observed warming, and understanding of the climate system. It's not really new. It's the same thing that was said in 1990, but now framed with a better understanding, perhaps, of how decision makers would appreciate the information. And I'm going to return perhaps a little bit to this. So let's go a little further into the evidence of these statements and try again from the real basics that in the most recent report is the way of looking at the climate change that we've observed. Then warming of the climate system is now considered to be unequivocal, which in basic terms means that we haven't seen anything like this before, and we are as certain as we as scientists can get on that we are seeing this happening. And since 1950, many of the observed changes are unprecedented over decades to millennia, meaning that if we look at various types of record, we can see that the rate of change is faster than we can induce from reconstructions of temperature and various other means. Then the changes are really much bigger than anything else seen before. And the atmosphere and the ocean have warmed. The amounts of snow has diminished. The amounts of ice has diminished. We've seen an increase in sea level, and along with this, concentration of various greenhouse gases has increased. And an important aspect of this, which was dealing a little bit with the highlight I showed before about the temperature not constantly on the rise, is that we also now very certain that ocean warming dominates the increase in energy stored in the climate system. And that is, of course, a very important aspect when we want to explain why climate is not just warming as a one-to-one response to the concentration in the atmosphere or the emissions. So let's take a closer look on the observed changes, repeating the graphs I showed before, but this time more focused on the regional variations in this picture, because while the global temperature is a sort of robust measure of how the climate system reacts to increase forcing from various constituents in the atmosphere, then it is where we live that the changes are experienced. In fact, you could argue that the global mean temperature doesn't really mean anything, because there are very few places where the global mean temperature is realized. What we realize is the temperature just outside, if not within the room, but outside at least, this is where the atmosphere, the climate system is functioning. And this diagram also shows the distribution of where we actually have good records of what has happened in terms of measuring temperature. So nearly everywhere there are reddish colors here. This is the temperature change over the last century, basically. White areas, that's where we have insufficient information to cover that long period. And the colors may be a little dim in the room, but the reddish to the dark, that's temperatures. The warmest, the biggest increase has reached more than 2.5 degrees. And there are actually a few places that have actually cooled over the last century, a little south of Greenland and in the central US. But many places, temperatures have risen more than 2 degrees. Along with that, we evidence that if we look at the end of the winter season for snow cover, there are measurements across Eurasia and the North Americas that how far south latitude we actually have snow cover. And that reconstruction of data since the early 1920s is showing that we, towards the end of winter, is seeing a reduction in the area of snow cover. It's important to notice that this is, of course, clear that it is warmer, we will melt more snow, but it's also an element that more snow you could expect in a warmer world, sometimes also a change of precipitation and therefore the snow cover. So this is not self-evidence that this would be the case. Likewise, we also made good estimates of the amount of sea ice in the Arctic, particularly within the satellite era, which is since 1979. But there are reasonable reconstruction going back, further back, at least within the 20th century. And the summer extent of sea ice in most recent years is only half of what it was in the beginning of the last century. And we have seen some episodes where we really lost dramatic amounts of Arctic sea ice. And this, of course, is also a consistent picture with a warming world. We've also been able to measure the heat content of the oceans. You should remind you that warming up 1 gram of atmospheric air is much easier than to warm up a gram of water. So the energy that you have to put into warming the ocean is much larger, 1,000 times larger than it is to warm up the atmosphere. And for that matter, it's difficult to measure the temperature increase in the oceans. But this has been done reasonably accurate within the last 50 years, and it's clear that the heat content in the ocean worldwide has gone up. Along with that, we also have good estimates of how sea level have changed, and in particular within the last, again, some 30 years. I'm just blowing into this, I don't want to do that. We've seen from satellite estimates very accurately that sea level is globally rising. And when we combine that backwards in time, we've realized that the global level of the sea level has increased by some 16, 17 centimeters over the last century. Now this is actually varying quite dramatically, so despite the fact we're not going to see council meetings below the sea in Sonderburg or anywhere in Europe for that matter, this actually reflects that there are areas where the sea has risen much more, in fact more than half a meter, and other places where there is a drop in sea level. This is related to other things than global warming, but over an average, the sea level has already risen quite a bit. And what is this? Well, from all the research that's going into trying to figure out how we can get that information related to the change, in particular the change of what we do with the atmosphere, then the human influence has now been detected in warming of the atmosphere, the oceans, changes in the global water cycle, reductions in snow and ice, global mean sea level rise, and actually also changes in some climate extremes. And those were basically most of what I just showed you, but the tools that goes into this, and this is where a big effort over the last decades have gone, that is to develop very comprehensive climate models that is capable of portraying the climate in great many details. This is showing global averages of land surface and land and ocean surface to the left of, in black, the temperature as it's been observed, and the blue and pink or red curves are indicators of how climate models reproduce the most recent temperature development. And with models we can make many experiments with the planet. We only have one, and the experiments then can be done that in a way that we, for example, test the hypothesis that, well, everything we've seen is a natural phenomenon. We can reproduce the temperature by feeding into our models information of how the sun is driving us, how the aerosol from volcanoes, and a number of natural phenomena. This is the blue curve, and then we can make another experiment by which we also introduce changes of the greenhouse gases in the atmosphere and other components that humans are influencing, such as land use change, aerosol loads, and a couple of other things. And the point is that if we look at this at a very large scale, we can only explain the most recent 50 years deviation from a constant climate by introducing these anthropogenic sources of change. And that goes with the heat content in the ocean too. Even more, and this is a more messy diagram, but this just to show that it's not just the global numbers, it actually catches up pretty realistically even when we go continental scale. And that is of course important to realize that a lot of what we've observed, including the variability from one region to another, is to a large extent explained by the anthropogenic source, that is the human influence on climate. And not only that, we also can see that the models are at the stage where, at the continental scale, they do a reasonable job. And this, of course, is important if we are to have any confidence in projections for the future. So that's what I'm going to take you to now. And there it's clear that continued emissions of greenhouse gases will cause further warming, will cause changes in all components of the climate system, and limiting climate change will require a substantial and sustained reduction of greenhouse gas emissions. Or more precisely, the cumulative emissions, they largely determine the surface warming by the end of the century, and actually also beyond. Remind you that in previous IPCC reports and in the community as such, we tend to look at the horizon that only go to the end of the century, but we are in many aspects already playing the climate game for not only this century but the coming many centuries. And that means that to handle this, it requires a multi-centennial scale to look into it. This is then showing using climate models to calculate what the global future would look like, and this is showing the global mean surface temperature change for a number of scenarios, which I won't have time to go into the details, but there are 4 scenarios that are picked, which is they have the name representative concentration pathways, and the low scenario is one which is constructed in a way that it can allow the global temperature to stay below 2 degrees by the end of the century. The others are taking different pathways into the future in terms of socioeconomic developments, and I will not go into the details about these, but the important thing is that some of them have been allowed to run freely into another 200 years, and in the worst case scenario you may say that if we take on board, assuming that all models are equally valid, then the projections suggest the temperature could increase as much as 12 degrees by the end of the 23rd century, which is really a different climate than anybody can think of. This is coming back to this diagram again, because now the colors of the projections can be seen from these scenarios that I just showed you, so that the decades ahead, they actually assume for the 2 degrees scenario that within the next, by 2050, we basically ceased using fossil fuel, at least netto-wise, whereas the other ones will, after 2050, allow for continued emissions. And what you can see there is that the dark blue curves, or the dots, they are just lining up next to 2 degrees. And the other ones are, if you can see it, there is a square which is saying this is the level we reach by 2050. And you can see that they are basically suggesting that we are surpassing the 2 degrees by 2050 if we are to follow other tracks than the very low emission scenario. And along with that, there are projections also on very large scales for sea level, and this is important in our part of the world, particularly for Denmark with a very long coastline, that within the next 100 years, the difference between a low emission scenario and a highest emission scenario is not that big. It looks like there's a big uncertainty here, but the important thing to notice here is that even at the low scenario, we are actually seeing considerable increase, and this curve does not stop rising when it goes beyond the 21st century. So there's actually, even with a 2 degree scenario, the chance that we can reach within centuries the meter level. And of course we have time to tackle it, but it's to keep in mind that long-term planning needs to look into this. And And this does not even take into account surprises such as the collapse of the West Antarctic ice shelves, which we don't know exactly when that could happen. And if that happens, we know it will result in relatively quick, very high increases of meters in our part of the world. And just to put the urgency in this is, that, of course, realizing where we are on track in terms of these scenarios. And this is just from the Global Carbon Project showing the estimates of the emissions as they are today. There is some discussion about last year's actual level, and there might be some revisions to all these total values, but we do know the concentration, not the emissions perhaps accurately. But it's important to see how these match with these RCPs. And right now, the track we are on is really very clearly the high end of the scenarios that has been constructed to assist assessing what type of projections we are heading. Now, the climate system is not about global temperature, nor is it about global sea level. These are sort of icons for what's happening. It's in our backyard that this is important. So the impacts are really different depending on where on the planet we are. And to the left, this is just showing progress between the previous IPCC report and the present. The CMIP3 data, top row is climate models as they were like 10 years ago, and the most recent one on the bottom row. Here, everything is scaled to 1 degree warming. And the patterns of change here illustrates clearly that the warming is going to be stronger polewards, and there's more warming over land than over ocean, and a number of regional deviations. To the right, equally important is that we will see changes in precipitation, and these patterns are of course very important. So it's not just about the mean, and here it is where it's the brownish colors, less precipitation than blue, that's where there's going to be more. In general, the picture is that where it's dry today, it's going to be even drier, and where we have plenty of water today, we will continue to have that and even more. Just to wrap it up with a couple of illustrations of what this means is that if we look at a European scale, this is trying to illustrate how the scaling at a certain temperature with a number of climate models, actually regional climate models that we nowadays use to zoom in and get more information about the regional scales. To the left you see upper row, that's temperature, wintertime and summertime temperature, as it increases the scaling with the global temperature increase for Europe, and the lower one is showing the change in precipitation. So what you see there is that in general we will get a moister Europe in the winter, but we will also tend with the higher and higher temperatures to get into a drier. And what more interesting is, of course, rather than the mean, is to look at things that are extremes, and this is showing the same kind of scaling with global temperature, the change in the 100-year return value of extreme precipitation, in this to the left for Europe and to the right for Scandinavia, and the bottom one is a more sort of a little bit ridiculous, a 10,000-year return period. But the important thing to note here is that if we look at the extremes, what is a 100-year event today with a 4 degrees increase, that would be more like a 25-year return period. And if we went to a 10,000, that is something extremely rare, that would actually come about with 6 degrees, it will only be already be something like every 100 years. So the more extreme they get, the more likely it is that we're going to see them compared to how we see them today. And this is, of course, not only here, this is all across the world. So the statement that the weather is getting wilder is a clear and evidence that is within the information. And by that, I come to my conclusions. So thank you for your attention.